Hello friends, hope you guys are doing well. Today we are going to know about digital comparator. You already know comparing numbers is one of the fundamental topics of computer. But have you ever wondered how a circuit actually decides whether one binary number is greater or less or equal to the another number? Today in this video we will learn that. Let's get started. So let's start with the 1-bit comparator. Block diagram of 1-bit comparator is like that. AB, and the outputs will be A equals to B, A greater than B, and A less than B. This is 1-bit comparator block diagram, and its truth table will be like that. As we are comparing two numbers with 1 bit, so the rows will be 4. 0 0 0 1 1 0 1 1. Now we have to check which conditions are true and which are false. So for the first case, 0 equals to 0, this is true, so 1. The second case, that is false. Also for the third case, that is false. And for the last case, that is again true, 1 equals to 1, so 1. Here this is false, this is false, this is true, so 1, and this is again false, so 0. And for the last case, this is 0, this is 1, and these two are 0, right? Now we have to think how to implement this using gates, our logic gates. Let's see that. We can implement this A equals to B operation using XNOR gate. Now why I am saying XNOR gate? Because the truth table of XNOR gate is, if X and Y is the input, 0 0 0 1 1 0 1 1, then and Z, if Z is output, then for only the same inputs XNOR gate gives true, right? So when this condition and this condition is applied, it will provide true. So this one and this one will be 1, and these two will be false. So to prove A equals to B, we are taking XNOR gate like this. A equals to B. And for the second condition, A greater than B, this can be implemented using A B bar. If you put and check, you can find what is happening. For this condition, when A is 1 and B is 0, here it will pass 1 and it will pass 0. For NOT gate, it will be 1 and 1 and 1, and the answer will be 1. So this will be true. And if for the other conditions, the A will be here 0. For the next condition, this will be 0. And for this condition, A is 1 but B will be 0 as there is a NOT gate. So ultimately only for A greater than B condition this will be applied. Now let's see the third condition. A less than B. This operation can be implemented using A bar B. Like the previous one, this one is like the same. If you check, you can see the results. For only this condition, you can see this will give 1. And for another conditions, it will give false or 0. So now let's see the circuit diagram using these gates of 1-bit comparator. So the circuit diagram of 1-bit comparator will be like that. A, B. These are two inputs of 1 bit. From here, there will be a NOT gate. This is for A greater than B. Checking. This is for A less than B checking. And this one is for A equals to B. If two digits are equal, this will give 1 and the another 2 will give 0. Now let's go to the 2-bit comparator. For 2-bit comparator, there will be 2 bits. For A, this will be A1, A0, and for B, this will be B1 and B0. So the condition A equals to B will satisfy if A1 is equal to B1 and A0 is A0 is equals to B0. As we know from the 1-bit comparator, we can write this equal to expression using XNOR. So the final expression for 2-bit comparator equals to will be A1 XNOR B1 and A0 XNOR B0. For the second condition, A greater than B, A1 must have to be greater than B1, or if A1 is equals to B1, the last bits B0 among A0 and B0, A0 must have to be greater than B0, right? So the final expression for this will be, for greater than, we have previously know that the greater than can be represented as A1 bar dot B1 plus a1 x nor b1 into a0 bar into b0. And the third condition is a less than b. So for less than condition, a1 must be less than b1, or if a1 is equals to b1, then a0 must have to be less than b0. So the final expression for a less than b will be a1 dot, oh sorry, there is a mistake. For greater than, this will be a1 dot b1 bar and a0 dot b0 bar, and for less than, this will be a1 bar dot b1 plus a1 x nor b1 into b0. Now let's see the circuit diagram of 2-bit comparator using AND, OR and XNOR gates. 2-bit comparator diagram. A1 B1, A0 B0, this is for the equal to condition. A0 B0, A greater than B. This circuit is for A greater than B. This one is for A less than B. Is greater than B0. If these conditions are shown, then we can say that A greater than B, right? So if we write the expression will look like this: A greater than B, A3 B3 bar plus, for greater than we have used the previously A into B bar, plus for OR A3 equals to B3, again we will use XNOR sign, B3 and A2 greater than B2. For greater than, we have used A dot B bar, A2 dot B2 bar, plus again for equal to A3 XNOR B3, A2 XNOR B2 and A1 dot B1 bar, again or A3 XNOR B3 and A2 XNOR B2 and A1 X NOR B1 and A0 dot B0 bar. This will be our expression for A greater than B. And the third expression will be for our condition A less than B. For A less than B, the conditions which must be satisfied is A3 must be less than B3, or if A3 is equals to B3, then A2 must be less than B2, or if A3 equals to B3 and A2 equals to B2 and A1 is less than B1, then also this can be said. Or if A3 equals to B3 and A2 equals to B2 and A1 equals to B1 and A0 is less than B0. So for all these conditions, this will satisfy, right? The final expression of A less than B will be A3 bar B3 plus A2 bar B2 into and A3 X naught B3, or A1 bar dot B1 and A3 X naught B3 A2 X naught B2, or A0 bar B0 into A3 X naught B3 A2 X naught B2 and A1 X naught B1. So this is our final expression for A less than B. So this is our three expressions to calculate the 4-bit comparator. To calculate or compare 4-bit, as far as you go, you will see the logic expression gets massive. I just four, shown in the 4-bit comparator, and the circuit will be complex also. Like you can see here, to make it simple, we use 7485 integrated circuit. This chip packages all that priority logic into one small 16-pin device. If A and B are two input, it takes 4 A bit and 4 B bits and gives output. As we know, there are three outputs: A equals to B, or A greater than B, or A less than B, right? It will give one output, obviously, three of them. Now let's see the block diagram of this 7485 IC. Comparator, then it is easy to make. Just see. Draw two 4-bit comparator. Three cascading inputs and three outputs. 2, 3, 4. 2, 3, 4. 2, 3, 4. 4. 7, 4, 8, 5, IC. So for 8-bit comparator, the first IC will calculate the LSBs, least significant bits, and the second IC will check the MSBs, most significant bits. So the most significant bits are, if there is 8-bit number, so for A, like it will be A7, A6, A5, A4, A3, A2, A1 and A0. So most significant bits of four most significant bits of A is A7, A6, A5, A4, right? So A7, A6, A5, A4. And for B also, it will be B7, B6, B5 and B4. And the least significant bits are the last 4 digit bits, A3, A2, A1, A0 and B3, B2, B1, B0. Here also, for the first chip, the cascading inputs will be 0, 1, 0. The output of this chip will be connected with the cascading inputs of second chip. This is how the circuit is made. This side of chip will compare the LSB and this side will compare the MSBs, and the final answer will be obtained from here. Okay, this is our 8-bit comparator.